So today I'm going to talk to you about a lecture about demystifying artificial intelligence. Basically just a 101 on neural networks. So I'm going to get right into it. Okay, so this is a 7. It's poorly written. It's a handwritten drawing, and it is at a very low resolution of 28 by 28 pixels. But it's easily recognizable as a 7, and your brain has no problem recognizing this as a 7. And your brain is incredibly clever because it can recognize this as a 7 as well as this. Yet, if you look at the exact pixel value of each image, they are very different from another. The specific photoreceptors in your eyes that fire when looking at one 7 is very different when looking at another 7. However, your brain is still able to correctly identify each of these as sevens effortlessly. But if I asked you to sit down and write a program that takes the grayscale values of each pixel in this 28 by 28 grid, with 0 representing white and 1 representing black, and output a digit between 0 and 9, the task would be downright impossible. And that's where neural networks come in. So there are many different flavors of neural networks in existence, and you may have heard of some of these. Some of them include convolutional neural networks, convolutional neural networks, or CNNs, which are good for handling visual data, like facial recognition to unlock your phones. Then there's long short-term memory networks, or LSTMs, which are good for sequential data, like speech-to-text for automated subtitles in YouTube videos. But for now, I'll just be talking you through the vanilla neural network and how it recognizes handwritten digits. Many of you may have heard that neural networks are inspired by the brain, and the brain is made up of many neurons. But what is a neuron in this context? For now, I just want you to think of a neuron as something that holds a number between 0 and 1. Our input image is a grid of 28 by 28 pixels that contains a number between 0 and 1. Remember that the number here is the grayscale value of each pixel, with 0 representing white, 1 representing black, and everything in between representing the gray level. We can think of each of these pixels as neurons because they hold a number between 0 and 1. The number that each neuron holds is actually called the activation. It may help to think of a neuron as being lit up or activated when a number is higher. So 28 by 28 makes 784. So these 784 neurons is what makes your first or input layer of a neural network. And just for information, this isn't exactly drawn to scale. As you can see, there's only 6 neurons I've drawn here, but I can't fit 728 on a page. That's why I left it at this. Then the last or output layer only contains 10 neurons, each representing one of the digits from 0 through 9. And once again, I've only drawn 3. That's just for aesthetic reasons and just to fit it on the page. The activation of these neurons are once again going to be between 0 and 1. And it represents how confident the neural network is how confident the neural network is that the input image corresponds to a particular digit. As you can see in these examples, for the first image, 7 is lit up the most, but you can also see that 1 is a little lit up as well, because that does look somewhat like a 1. In the second image, 9 is lit up the most, but both 6 and 8 are also slightly lit up because it has to draw a 9, you need to draw sort of a loop, and the 6 and 8 also has loops in it, so that might be the case. For the final image, it looks like a weirdly drawn 4, but really kind of looks like a 9 as well, which is why both 4 and 9 are lit up, but it's mostly the 4 that's lit up. In the middle, between the input layer and the output layer, we have the hidden layers, which is where all the magic happens. Unlike in the input and output layers, the number of hidden layers and the number of neurons in each hidden layer is somewhat arbitrary. And I say somewhat arbitrary because there are some guidelines and heuristics that you should follow. For instance, the number of neurons needs to be more than that of the output layer, but less than that of the input layer. The number of neurons in each subsequent layer must be the same or less. So basically, as you can see, it sort of gets funneled in towards the end. And the complex problems generally require deeper networks. So more hidden layers, simpler problems require shallower networks, maybe just 1 or 2 hidden layers. But there are heuristics like that you should follow. But ultimately, the number and size of the hidden layers are chosen through experimentation. You generally try different configurations to see what works best for your model, and you evaluate the output. The activation of each layer determines the activation of the next. And when we reach the output layer, the brightest neuron represents the network's consensus on what digit the input image corresponds to. So if we input an image with a 7, if the network is trained well, the neuron corresponding to 7 should be the brightest. So here I've just drawn 3 neurons at the end, 6, 7, and 8. And as you can see, 7 is lit up the brightest in the final layer. But why exactly is it organized into layers? Well, when we recognize digits, we look for certain components. For a 7, we might look for a horizontal line near the top of the image, as well as a vertical line down the center of the image. And in some cases, depending on how people write their 7s, you might also look for another horizontal line near the middle of the image. Likewise, there are many other components that help us recognize digits, like, for example, a loop for a 0 or a 6, 8, or a 9, and various other components as well. You can think of the penultimate layer, the final hidden layer, as having neurons that correspond to each of these components. So as you can see, drawn inside each of the neurons of the final hidden layer. I've drawn sort of at the top. I've drawn the horizontal line. In the second one, I've drawn the vertical line. In the final and the third one, I've drawn the middle horizontal line. So you can think of it as those neurons corresponding to those particular components. So if you take another step back, the previous hidden layer can be thought of as having neurons that correspond to various subcomponents. So maybe you can break down that horizontal line into 2 pieces, one in the top left quadrant and the other in the top right quadrant. But I mean, this is just it's a good way to think of it so that you can understand it a bit better. But in reality, what each neuron represents isn't nearly as clean as this. If you were to dissect a neural network and look at what each neuron is computing, it kind of looks like nonsense to us, but obviously it makes sense to the network. In some cases, though, you can sort of see what it's doing. It's looking for certain edges in certain parts of the image, but in most cases, it isn't what we think it would be. So when you show the network in image, the neurons corresponding to the subcomponents and the components in the hidden layers will light up, leading to the neuron corresponding to the correct digit in the output layer lighting up, like so. But I mean, yeah, as you can see over here, all the components, well, the only ones that I've drawn are the ones relevant to the 7, are all lit up. This particular 7 doesn't have a line drawn through the center of it. So the neuron corresponding to the horizontal line in the middle hasn't been lit up. But how does the network ensure that the correct neurons are lit up? So I previously asked you to think of a neuron as just something that holds a number between 0 and 1. It's activation. But I'm now going to expand on that and say that aside from the input layer, the activation of a neuron is a function of the activations of all the neurons in the previous layer. More specifically, weighted sum and a bias component, as you can see with the equation of written at the top there. And this weighted sum plus bias component is then fed into a function that essentially scales the output to a value between 0 and 1. In the past, they've used what's called the sigmoid function for this, but more recently they've used we've been using the rectified linear unit, or ReLU. These weights and biases can be adjusted so that the neuron only lights up when the particular subcomponent or component that it is looking for is present. Note that just one neuron in the first hidden layer has 785 weights and biases, or 784 weights and one bias component that can be adjusted. So as you can imagine, when you consider the entire network, there are literally thousands of weights and biases in just our example. And this does scale up rapidly with the more complex a neural network gets. I mean, for instance, GPT-4 has over 175 billion of these parameters. So let's take the example of a neuron in the first hidden layer looking for a horizontal line near the top of the image. So as you can see on the diagram on the right, so that is the grid of weights essentially. Most of the weights are 0 because this particular neuron only cares about the region near the top. And near the top, there is a rectangular area of positive weights depicted in green here, bluish green, or like turquoise. And it's sandwiched with a layer of negative weights on the top and the bottom, depicted in red or orange here. And this will result in a value close to 1 if a horizontal line is present, and a value close to 0 otherwise. You can sort of overlay these two images and do the maths for yourself and see. I mean, basically, if the greens represent large positive values and the reds represent large negative values, and you do the multiplication and add it all up, you'll see that unless there is sort of a horizontal line at the top, it's not going to result in a large positive value. Otherwise, it just end up being 0. So all of this assumes that the neural network already knows what to look for. It still begs the question, how does the neural network know how to adjust these weights and biases? Essentially, how does the neural network actually learn? So this requires 3 things: training data, a cost function, and an optimization algorithm. The training data, as you all know, is nothing too complicated. It's basically thousands of handwritten digits and their corresponding labels, as you can see over here. The cost function, though, is a bit more complicated. I mean, I'll just give you an example of, well, for those of you with pets, you have to potty train them. And it's always difficult, you feel bad to scold them, but you need to. They give you those puppy dog eyes. But, if they pee inside the house, you're probably going to shout at them to make them feel bad. If they pee, say, on your bed, you're going to probably be even madder and shout at them even louder than that. But if they pee outside in the garden, you're going to say how good they are and pet them and make them feel good. And that's essentially the role of the cost function. So the cost function can be defined in many different ways, depending on how you want to motivate the neural network to learn. In our example, however, we are going to use the sum of squared errors. So this, what I've drawn in this table here is an example of the cost function. So you can see the input image on the left. You can see the output layer neurons all lined up there, and actual values corresponding to it, not just the brightness of it. And then you have the actual correct label. So it should be a 7. So everything is 0 apart from the 7. And you compute the cost by just taking the square, square of the errors, and you sum it all up and get a final cost value. So you notice that when the network confidently classifies the image, in this case, it assigns 0.99 activation to 7, the cost is small. But when it's not so sure, for instance, if some of the other values were maybe closer to 0.5, 0.6, and maybe the 7 was at a 0.8 or something, you can see that the cost will be small, even though it does ultimately classify the image correctly. So basically, even though it does get the image, it does get the classification correct, the cost function does penalize the network and forces it to improve upon it even further. And of course, when it is wrong, the cost is going to be even larger. And just to note that this cost is the cost of the calculation I've done here is just for one example, but generally you average the cost across the entire network. Sorry, the entire training data set of the network. So in order for the network to get better at its task of recognizing handwritten digits, it needs to minimize this cost function. That's where the optimization algorithm comes in. For example, we will discuss one of the simplest ones, gradient descent. So recall that this neural network has thousands of weights and biases that can be adjusted. And for the sake of simplicity, because it's really hard to draw it on a 2D piece of paper, let's just assume that it has just one weight that can be adjusted. So in this graph, on the x-axis, I have the weight that can be adjusted, the value of the weight that can be adjusted, and on the y-axis, I have the cost. And as you can see over here, there are 3 minimums, and there are 3 minima that you can see. And for those of you who are sort of remembering your older maths classes, you might think that you can solve this analytically by solving for when the gradient equals 0. But the thing is, in the case where it's in neural networks where you have thousands of weights, it's actually not feasible to solve it like that. So instead, we have to solve it by systematically trying different weights, sort of like a trial and error, but not exactly trial and error, because trial and error would imply that you're just shooting in the dark. But here there is like a systematic approach to this. So first, you want to initialize the neural network with completely random weights and biases. There are different choices for how you can initialize it. Maybe you can initialize it with zeros, but just for the sake of this, let's just say you initialize it completely randomly. Then you run all the training examples through the network and calculate the cost, and you arrive at point A in the graph, for example. Then next, you would want to calculate the gradient of the cost function. You do this by you remember your maths. You just calculate a little delta to either side, and you know the gradient. And then you can determine which direction gives you the steepest slope, steepest downward slope. So in this case, it would be to the right. So you need to increase the weight. So then you adjust the weight by, in this case, increasing it, and you take a small step in that direction. After that, you rerun the training examples through the network and recalculate the cost, and then you arrive at point B in this graph. So we repeat this process. You calculate the gradient, take a step, move the weight in that the direction of the steepest descent. And then you arrive at point C, and then eventually you arrive at point D, and which is the local minimum. And also as a side note, it does help to make the step size proportional to the size of the gradient, so that you don't overshoot the local minimum. So when you're at point A, you'd probably take a larger step. Well, point A and B seem to have roughly the same gradient in this drawing. So you take about the same step size, but once you get to C, it's sort of a bit flat. It's kind of flat, right? So you take a smaller step size then to stop yourself from overshooting. Of course, this is just a local minimum. I mean, in this particular graph, it does happen to be the global minimum, but there isn't a guarantee that it'll always reach the global minimum. And unfortunately, there is no reliable way to do this. I mean, you could reinitialize the network completely randomly again, and maybe you start at a different point that will help you reach a different minimum, and then you can test both of them. But it's not always feasible to do. I mean, especially when you're spending millions on compute costs for processing all the training examples. You don't want to have to just do them again from scratch just because you're not sure whether you hit a local minimum or not. But usually just hitting the local minimum does do the trick. But anyhow, this is how the network learns. So all that's left now is for you to just run some test data through the network and evaluate the results. The test data, as you can see, is basically the same as your training data. The only difference is that your network has not seen any of the test data before. So you can evaluate the results and see how well your network does. And well, that's 101 on how neural networks work.